Alright, so now that we know our rules, and we've looked a little bit at these exponential functions and whatnot, I want to actually make a connection here with something that we've done in the past, and that is this compound interest. You might recognize the compound interest formula that we see here, and I want to point out a couple of things in case you haven't seen this before, but we have here a compound interest formula. If it's compounded n times a year, and we're doing this for 1 year, okay, now notice there is no n times t here, because here they're assuming t is 1 year, okay? But can someone explain to me, in this case, we have an 8% interest compounded n times a year. Why do we divide r by n? Can anyone explain that to me?
Is R... what is R again?
R is
the rate of
this interest rate.
Because R is based on 1 full year, right? So
yes.
And because it's to the power of n instead of the amount of years, you have to divide it into each chunk for the amount of times.
Exactly right, okay? When we're dealing with compound interest, you have to consider the rate not as an annual rate, but you have to look at the rate per compounding period. It's just like what we were talking about earlier when we were talking about half-life. That 50% decrease in half-life is not per year, it's per whatever the half-life is. And that's why the formula had you doing 0.5 times, or 0.52 the t divided by k power, because you had to convert time into half-lives. Well, here we have to convert our rate from an annual rate to a rate per compounding period. All right? So if n is 1, then that means we're only going to compound once a year, so that 8% interest is the rate per compounding period. However, if we have 2, I'm not going to make 8% every time it compounds. I'm going to make 4% every time it compounds. If n is 4, 8 divided by 4, I'm only going to be making 2% every time it compounds, every 3 months in this case. All right? If it's 12, 8 divided by 12, I'm going to make 2/3% every month. Okay? Or if n is 365, if I'm compounding daily, all right, I'm not going to make 8% a day. I'm going to make 8 divided by 365%. Okay? Whatever that equals. That's the percentage I'll make every day. All right? So that's why we do that r over n. That's important to understand. That'll help you really remember that in the future if you ever have to, or as you have to work with this again in the future.
I'm having trouble remembering if you compound it twice. So you just tax or just receive extra every 6 months in a year. What percentage are you getting back?
Well,
Each
if
time?
you're making an 8% interest rate, then the first 6 months you're going to make 4%. Okay, so like in this case, 1,000 times 4%.
So the 8% will be divided, right?
Yeah, it'll be divided. That's what this r over n here is. Okay. 4% of 1,000 would be $40. So in that first 6 months, you would make $40, which means now you have $1,040.
Oh, but then you're going to take the percentage of 1,040, which is going to be more.
That's right. So this time you'll make $40 or $41.60.
Whoa.
So in the end, you're going to have $1,081.60.
And if you hadn't done this twice, only once, you would have got $1,080.
You would have only gotten $1,080, yeah.
And if you compound it every millisecond, every infinitely, what is it going to be?
The more you compound, the more you're gonna make.
But
Okay.
What is the max involving the
Approaching the value, he's asking.
like
I'm
as
sorry,
you
what?
approach infinity
Oh,
division?
that's actually what we're gonna develop here.
Okay.
Okay, so let's actually go ahead and get the calculators out here for a second and go ahead and find these 5 different values. We'll fill in our table and then we'll look down at the bottom. Alright, so if we graph or make this, the amount after 1 year is 1,000 times 1 plus, make sure you put a 0.08, you don't want to mess everything up doing 80%, over n to the n. Alright, so we already said that you would get 1,080 after a year if it's not compounded at all. If it's compounded twice, we figured out it would be 1081.60. How about 4 times?
I think it was
1082.4?
4.
Okay.
4.3. 0.43.
0.43.
Doodles.
Okay. Round to the penny. How about if we do it monthly?
1082.99. So I guess like it was like 0.99999. So I guess it's like 10.83. Or excuse me, 1083.
Okay.
My table just says
1083.
1083.
Okay. And then how about 365 if you did daily compounding? 278. All right, so we'll round that to the penny, so 28 cents.
That was also the answer that I got.
Okay.
So it doesn't make much difference if you compound.
So it's not going to make an enormous amount of difference. Now this is only after 1 year. If you carried this out for 20 years, then that would be the difference here. You would see would be a lot greater.
Wait,
Okay.
what's 20 times 265? 730. What if we plugged in? Oh, that was really bad math. 7,300. I'm doing that. Hang on. 70.
Well, no, you would need to raise the 1 plus 0.08 over n.
Instead of 365, it'd be 7,300, right?
Oh, you're multiplying by 20?
Yes.
Yeah, 7,300.
30 minutes.
I'm doing that. Hang on.
Don't make the 0.08 divided by, keep that as divided by 365.
Oh, why?
Because you still want it compounding daily. Okay.
Alright, you ready?
Alright, what do you have?
You get, it's the wrong button. Hang on. You get 49.52. So almost 5K.
49.52.
0.16.
Okay. As opposed to if I compounded it once a year, and I just did 1,000 times 1.08 to the 20th power. Okay. I would only have $4,661 about. Okay. So you'll see here the difference after 1 year was only about $3.28. After 20 years, the difference is almost $300. Okay, so the amount that you compound does make a difference. It's just it takes time to make a real significant difference. Okay. Now, you guys were thinking this was good. You know, the more we're compounding, we're making more. Well, let's think about this. Okay. If we have this same function, okay, or a similar function, the 1 plus 1 over x to the x, that's like the 1 plus r over n to the n, right? Okay. as x is getting bigger, it really doesn't matter what the rate is, right? Because that part, as x approaches infinity, is going to approach 0. So whether it's a 0.08 over x or a 0.1 over x, they're both going to approach 0 as x approaches infinity. Okay? Now, you'll notice here, if I get a common denominator, that would be x plus 1 over x. If I take the limit as x approaches infinity, I actually get the value of e. This is the definition of what e is. Okay, 2.71828 and so on. Alright? Now, you can see this. Some of you asked, hey, what if we made it compound more and more and more? Well, think about what we're doing here. Okay, here's the formula we started with. 1 plus r over n, 1 plus 1 over n over r, if you will. Okay? And we make this n over r. Alright, and notice I'm accommodating for the fact I'm dividing by r by raising it to the r power. So I haven't changed anything here. But notice now I'm making this n over r the x. Okay? And what's happening as that approaches infinity? In other words, as n is getting bigger and bigger and bigger, this n over r is going to approach infinity as well. Okay?
So that you can use e for whatever rate and n.
That's e. Notice it's p times e to the r. And that's for 1 year. If I wanted to do this for many years, okay, it would be
2 times
n times t. So this whole thing, okay, this whole thing would be to the t power. And there's your PERT formula from Pre-Calc Honors for continuously compounding interest. Okay? P times e to the RT. That's where that came from. Okay?
Could you explain why is that an x? Why is n over r an x?
We just changed variables to make it look pretty. And to make it match our value of e.
Yeah, but why is like you do not include r, you basically forget about it.
Well, because r is constant and n is approaching infinity.
Infinity over constant is still infinity.
Yeah, so we're saying, okay, as n approaches infinity, this whole ratio, n over r, which we're making an x, is going to approach infinity. So we're seeing it has the same structure as our definition for e. Okay, yeah.
If you wanted to calculate the rate, how much you're making if you're putting 1,000 every year, and not only the principal amount you start with, can you do that?
That you have to do with like a series, because you're changing, you would have to do the first $1,000 for the full amount of time, but the second amount is going to be for 1 year less. The third amount is going to be for 1 year less. Okay, you'd have to do that as a series. Okay. All right, but anyways, this is our where this formula comes from, the p times e to the RT that you used back in Pre-Calc Honors. But let's go ahead and use this a little bit. We're just getting, it's kind of just a little bit of review. So take a few minutes here. Go ahead and work with somebody, and notice here it says we want at the end of 5 years if the interest is compounded quarterly, monthly, and continuously. Okay? Alright, so let's take a quick look at these. Okay? Your amount after 5 years, we're starting with $2,500. We have 1 plus the 0.05 divided by n to the n times, if we're doing it for 5 years, we need to multiply this by 5, All right, because that'll tell us how many compounding periods we have. If we have 4 quarters a year times 5 years, that's going to make it 20 periods that we're dealing with. Okay? If it's monthly, that's 12 months for 5 years. That's going to be 60 times that it compounds. All right, so for A, the amount would be 2,500 times 1 plus 0.05 over 4 to the 20th power, because 4 quarters times 5 years is 20 quarters. All right, what did you get when you did that? 300 or $3,205.09. Okay. Can anyone else verify that?
That's right. 320509.
Yeah.
Okay. All right. Good. And how about B? 2,500. 1 plus 0.05 over 12 for monthly to the 60th power, because there's 60 months in 5 years. And what do we get?
I got 320840.
Okay.
Every day we live.
All right, then finally C. This is the function we just derived. It's the principal, the starting amount, times e to the r times t. So r is the 0.05 times 5 years. Okay, so this is going to be 2,500 times e to the 0.25 when you multiply that. And what does that end up giving us? 3210 and 6 cents. Is that right? Okay. And guys, listen, this is really the limit as the number of times we compound per year approaches infinity. Okay? So as we compound this an infinite number of times, that's what we're going to end up getting. Okay? Now, another example here, we have this logistic growth model with bacteria. Okay? Now, if you remember bacteria, or the logistic model from last year, this was a case, this is often used in things like disease or whatnot, or when you're filling something up. Okay? You have something that starts to grow what looks like exponentially, but then as it reaches capacity, it's going to slow down. Okay? You could model people coming into a stadium for a game this way. You could model growth of bacteria, because at some point there's not going to be, especially like in a little petri dish, there's not going to be enough room for more bacteria to grow. They use this for modeling outbreaks of different diseases. They call it a SIR model, sick, infected, or not sick and infected and recovered. I forget what the first letter stands for. Huh?
Resistant?
Well, recovered is also considered resistant, because once you get better, it's rare that you get the same thing again a second time right away. So, but anyways, they use these models for things like that. But this
susceptible, infected, resistant.
Susceptible, that's what it is.
I'm just guessing it's that. I don't know.
No, that's susceptible. I think is the right word there.
Total guess.
All right, but here we're going to look at the weight of the culture. Okay, this model, Y is the weight of the culture in grams, and T is the time in hours. Okay, so we want the weight after 0 hours, in other words, at the beginning. So if I plug in a 0 for T, what do I get in that model?
Zoom in a little.
If I plug in 0 for t,
1.25.
okay, I've got to get 1.25
Divided by 2.
divided by 1 plus 0.25, okay?
Oh.
So that is just 1. So 1 gram is how much this culture weighs after, or at the beginning.
And that is P. Yeah, P.
That would be our starting amount, yeah, if you were thinking of it in terms of something like that, of exponential growth.
So if you don't know
But-
P, you just plug in the unit.
Well, again, this is a different model, so P isn't exactly the same as maybe what we're thinking, okay? But that would be the amount at the starting time, okay? So then for B, after you plug in 1 hour, we'd have 1.25 over 1 plus 0.25 E. And if we plug in a 1, it's just to the negative 0.4 power. Okay? And then C, 1.25 over 1 plus 0.25 e to the negative 4th power. So we multiply it by 10. Okay? So what do we get here for B?
You got a 0.3.
1.071 for B. Okay, you got that too? Okay. And how about for C, if we plug in 10? 1.2443. Okay, anyone else get that? By the way, if you're punching in each of these individually, you're not working efficiently on your calculator, okay? Use your y equals, use that table where it asks for the independent variable and you can just type it in, or graph it and use trace, okay? We need to be getting comfortable using our calculators in these other ways.
There's a problem. How is, like, in the regular exponential problems, how is P not a variable? It is a variable, is it not?
P was your starting amount. That's constant. Whatever you put in is whatever you put in.
Yeah, but if we choose to do it as a function of two variables, it's going to make no difference except on the graph. Because we still need to input P, and imagine a situation where
yeah, you have to input P. Each situation is going to create a different model. So yes, P is something that you could plug anything into, but it's a matter of once you have the situation, you're going to know what P is. Okay, so now notice here it says that to find the limit as t is approaching infinity. Okay? So for D here, we have 1.25, 1 plus, and now we got to think about what is this 0.25 e to the negative 0.4 t. What's that going to approach as t approaches infinity? E to the negative 0.4 t is going to approach
0.
It's going to approach 0. Okay? because this is a negative exponent, so it's going to be 1 over e to the infinity power. All right?
So will this be to 1, the whole thing?
The denominator will equal 1. Because we're going to have 1 plus
So this
0.25 times 0.
So the whole thing will be approaching 1.25.
That's exactly right.
So that's
1.25 grams.
the max value.
That's what it's going to approach. And actually, remember your logistic function, how it's has this asymptote up here, the way I drew it before. It looked like this. That capacity, maximum capacity, was that vertical asymptote or that horizontal asymptote up there. That's what it's approaching in this case. And if you have a really great memory, you might remember last year when we looked at logistic functions, the capacity was your numerator. The maximum capacity was your numerator. So if you're looking at a model for a stadium that holds 50,000 people, it's going to be 50,000 over something. Okay?
Yeah.
So,
Which makes sense.